Hey everyone, welcome back. If you missed the last two videos, I went through the IDE and just gave an intro to this series. So if you need to kind of learn your way around this AVB Robot Studio, that's what we're using for simulation here. Um, but we're about to just really get into the meat of things. So uh, here we go. This is a coordinate system here. You can see these three axes follow this coordinate frame here, this plane. That's my ground plane. So this is, the factory floor, the floor in your house or wherever you're playing with these robots. So um, they take three-phase power, so you're probably not going to be playing with one in your house. But either way, this robot, it's about 6 feet tall. It's a pretty big robot. But what I'm getting at here is this coordinate system in the y positive direction, that would be over in this area, and the y negative would be in this area. So that's with respect to the robot world coordinate system. So you can see there's a matching set of coordinate indicators down here that show this world coordinate system. So there's various ways to think about these coordinate systems, and the easiest one for me at least is world. So if you think about, what is a point in this system going to be referenced to, the base of the robot makes a pretty good default location, and really it doesn't matter a lot of times, because as long as the robot's repeatable to those points that you teach, then it should be okay. You don't normally often care exactly about the numbers, you more care about their relationship to other coordinate frames or to the robot itself or to the part. So we'll get into some of that calibration stuff later. But if you have a nice calibrated robot, which they come from the factory with a 000 point defined already, they're all closed loop encoders, basically. Some of them battery backed up, some of them not, but they all have brakes here. So when you take power off the robot, the brakes kick in, the robot holds its place, and then when you boot back up, everything should be good. So the robot knows where it is, and I mean, your program may not know where the robot is. That's a whole different topic altogether. But the robot at least knows when you say go to this point in the world coordinates, it'll go there. So a point that's 1,000, 1,000, 1,000 for X, Y, and Z would be just right above this section here. These are 1 meter tiles here. So we can go ahead and create that point though. We call that a target. It's a point that you're interested in. So that's different from a path. A path is a bunch of targets in a specified order with speeds and all that as well. So let's create a target here. Make it 1, 1, 1 meter, that is, and we'll give it a name. Actually, here we'll add it, and then we'll make sure it has a name. It'll auto-name these targets if you create a bunch of them. Give it a task for it to be in. This will only have one task in this system. And then work object. We only have one work object defined, which is the default one. This is a work object that sits at here. I believe Fanuc calls work objects user frames. So if you're coming from that world, that's work object and user frame are basically the same thing. As far as I know, I don't have a ton of Fanuc experience, but I've messed with them, and so you almost never want to use this world work object because that implies that everything out here is going to be calibrated perfectly to your robot. In the real world, that's not going to happen. But we're going to start there. So, and then insert move instructions in that if you want to put this directly into a path, you can do that. And so that's helpful if you're making a whole bunch of paths or a whole bunch of targets in order and you're expecting them to go to a path. You can do it right here. But let's not worry about this. This is not our path at the moment, just a point. So you can see this orientation basically matches this default orientation. So the closer I get to it, the bigger it'll get, hopefully. Let's see if I can make this extra large. Frame size large. Oh, it already was large. So if I want to view this robot at it, let's close it. We're not making any more targets. I can come to this thing and say view robot at target. So now it's put it there. And if you look at it, this flange is the point. Right at the center of this point is what the robot knows about. So it's actually here using its built-in kinematics to, or inverse kinematics, I think in this case, but it's using it to determine exactly what all these joint positions need to be to put this at the exact right spot. But well, we've only defined 3 degrees of freedom here. We've defined X, Y, and Z, but we have not defined the roll, pitch, and yaw of the system. So if if this thing is here, let me use something a little easier. If this roll of tape here, see if you can see that. If this roll of tape is a point in space, we've got Z-axis, X-axis, Y-axis towards the camera and further away, and then we have roll, which would be this direction, pitch, which would be this direction, and yaw, which would be around its own axis here. So what that means is that this point right now has a yaw, pitch, and roll value, but we didn't really define it, so it's 0, 0, 0. So what I can do is just come in here, modify target. I'm right-clicking this, so let me go back a tiny bit. This work object here is where all your points live, in the station at least. To be clear, this is just in the station that I'm in. So this target, I can right-click it, modify, and I can rotate it. I can offset it. I can set a new position here, of course, but I can rotate it. So this is important, and might make your life hard if you don't realize how this works, but I can rotate about any coordinate system. And so if I rotate around the world coordinate system, that's going to put a point right at the base of this robot, and it's going to rotate that guy up and around like this, which is almost definitely not, it's almost never what you want to do. I mean, you may need to for whatever reason, but typically what you want to do on a point like this is a local reference frame. And so that's saying from this very point where all 3 of these axis identifiers meet, that's its origin. That is the point, the location in space. And you want to rotate about those points. And so here I can specify, now this is to specify a rotation around a different point altogether, so that's confusing as well. But what you want is down here, if I want to rotate about X, I'll say 90 degrees, apply, and by 90 again. And so what that was saying is the target was out of reach in this output window down here, and essentially we've rotated that position around, and it can reach it from the top now instead of the bottom. So we're specifying this point's orientation in all 6 degrees of freedom now. And you can just change that point however you want. You can free spin it if you'd like. Here I'm actually rotating around the world frame, which is not good, but let's do local, and I can rotate that around here. So now if I were to turn off view robot at target and maybe grab this robot joint here, sorry, wrong one, there we go. So I've now defined this point here. This big ol' honker, I think that's an artifact, a graphical artifact, so don't get hung up on him. This is our point right here. So he's now been defined in roll, pitch, yaw, and XYZ. So the XYZ being the point, the roll, pitch, yaw is its angle about that point. And actually these systems technically use, you can reference it in multiple ways. You can reference quaternions as well instead of Euler, but I'm more used to working in these. So the actual point will be stored in quaternions. So just something to know. You don't need to worry too much about them necessarily, but you can see the difference between those two values. So we have our first point, and I think that about explains the 6 axis, the 6 degrees of freedom, and I'm at my 10 minutes. So we're going to move on to the different types of motion that the robot can perform, and we're going to run a quick path on the next video. So I'll see you over there.